Okay, ma'am. Welcome back. Now we are entering the second session of today. I would like to invite Mr. Abubakar P., Assistant Professor, Department of Mathematics of Government Engineering College, Palakkad, to introduce the resource person.
Thank you. Am I audible?
Yes, sir.
Okay. Welcome you all for the second session. It's my pleasure to introduce the resource person of the session, Mr. Vishnu Das. By the way, he is my classmate too. Let me have a brief introduction about the speaker. Mr. Vishnu Das is currently working as an Assistant Director of Education at online tutoring service platform Growing Stars. He earned his post-graduation in mathematics from Cochin University of Science and Technology. Previously, he had worked as an algorithm developer at ITI Limited, Bangalore, developing encryption-decryption algorithms for defense communication. He also worked as an assistant manager of engineering technology in Kennametal, Bangalore. Mr. Vishnudas received the Best Performance Award for design and development of an indigenous algorithm, which is the first block cipher algorithm developed by Research and Development ITI Limited. With these words, I welcome Mr. Vishnudas to this session. Also, I welcome all the participants joined in this session. Thank you all.
Good evening, everyone. Am I audible?
Yes, sir.
Yeah, okay. Thank you very much for the brief introduction, Abu. And thank you, St. Thomas College Math Department, for organizing and inviting me for the talk. Let me just open my presentation. Can you see the presentation?
Yes, sir.
Yeah. So I would like to start off with some block cipher techniques and in line with AES. So let me just start very briefly with an introduction of cryptographic algorithms. I think most of the things would be pretty familiar with all of you. So let me just start with what do you mean by an encryption? Hope everyone would be knowing that encryption is the process of converting information or data into a secure and readable form known as ciphertext to protect it from unauthorized access or interception. So it ensures that only authorized individuals or systems can access and understand the original data by using a decryption key or algorithm. So encryption plays a crucial role in ensuring the confidentiality, integrity, and authenticity of sensitive information. So it is used in various applications such as secure communication over the internet, for example, HTTPS, wherein we right now have an Google Meet, which is securely secured through HTTPS thing, and it is again done with the help of a block cipher. And something like secure to do secure file storage, to do password protection, and to have digital signatures. So additionally, encryption is a fundamental component of any secure protocols like SSL, TLS, SSH, and VPNs. So I'll be describing the same in the coming slides. So let me just briefly tell like what a cryptographic algorithm is. So it is basically a set of mathematical procedures or rules which is used to encrypt and decrypt data securely. So these algorithms form the foundation of modern cryptography and are essential for protecting the sensitive information. So there are several types of cryptographical algorithms and each serves different purposes. So let us just confine our discussion into symmetric and asymmetric encryption. So these are the two main type of encryption, wherein which depends on how the keys are used. The cryptographically secure keys are used for doing the encryption. So encryption could be categorized into symmetric one. The symmetric one would be the same key. From the name itself, it is understood that the same key is used for both encryption and decryption. So that's the name symmetric, because the same key would be using for the encryption as well as decryption. The sender and the recipient must have a shared secret key, which should be the same. The data is encrypted using this key, and the recipient can decrypt it using the same key. So some of the examples are advanced encryption standard, which we'll be dealing in detail today, and DES. The other form of encryption is asymmetric encryption, so which is also known as public key encryption, which use a pair of mathematically related keys, a public key and a private key. A public key is so what do you mean by a block cipher? A block cipher is a cryptographic algorithm that operates on a fixed size blocks of data. So encrypting or decrypting the data in these blocks. So that is what precisely a block cipher is. So you can mention the difference between a block cipher and a stream cipher, which operate on data streams bit by bit. The stream cipher would be the data would be operating bit by bit, whereas the block cipher, it would be as a block. So basically, a stream cipher you could just think of as a block of 1 bit. So let me just briefly introduce some of the applications which I mentioned earlier. Like data encryption is the very important thing wherein the block ciphers are used. So it is again basically it is the encryption of the private and sensitive data. So such as passwords, the credit card details, and other information that are transmitted or stored for a communication. So this encryption process converts a plain data into a non-readable and complex form. And the encrypted data can be decrypted only by the authorized person with the private keys. So other application is file and disk encryption. So the block ciphers are used for encryption of entire files of the entire disk, something you could file in the laptop, like you'll be able to encrypt the entire C drive or entire D drive. So it is possible, there are multiple softwares available. So disk encryption, which could be like BitLocker or TrueCrypt, also uses block cipher to encrypt data and make it secure. So other thing is VPN, the virtual private network, so which uses block cipher for encryption of data that is being transmitted between two communicating devices over the internet. So hope everyone would be knowing what is VPN. You might have heard that. This process makes sure that the data is not accessed by unauthorized person when it is being transmitted to another user. And the secure sockets layer, transport layer security. So these are the protocols which use block cipher for encryption of data that is transmitted between web browsers and servers over the internet. So this encryption process provides security to confidential data such as login credentials, card informations, which will be securely transferred. So another thing is the digital signature. The block cipher are used in digital signature algorithms to provide authenticity and integrity of the digital documents. So this encryption process generates the unique signature for each document that is used for verifying the authenticity and detecting if any malicious activities is detected. So let me just come to the main topic which I would like to discuss, just basically AES, which is Advanced Encryption Standard. So this is a block cipher, which is standardized, approved by NIST, and wherein a block of 128-bit plain text is encrypted with the help of 128 to 256 bit. It varies based on the range and the rounds, which is defined for the encryption function, and resulting into ciphertext. Am I audible to everyone?
Yes, sir.
Yeah, if there is any
Yes,
questions
Karthik.
in between, no, you could just raise your hands, or you could just interfere in
Excuse me,
between.
sir. Excuse
Yes,
me, sir.
please.
Mr. Kaushal Soni, will you please mute? Okay, sir, you may continue.
So the pictorial representation which deposites that 128-bit plain text with the help of key will be resulting into a ciphertext of 128-bit. So these are the generic structure of an AES, like rounds which are almost identical. The first and the last round are the little different. The square box which I have said that 128-bit plain text would be the input, and there would be a pre-round transformation, and then from there we'll be having the round functions like round 1, 2, etc., like which differs based on the key length, and the number of rounds in the AES would be 10 if we are taking the key size as 128. If you're going to encrypt 128-bit plain text with 128-bit key, and the rounds would be like there will be 12 rounds if the key size is 192, and there will be 14 rounds if the key size is 256. So the relationship between the number of rounds and the cipher key size varies. And this is an high-level description of how a round function or how an encryption happens in AES. So there would be the process. These are the steps which need to be undergone while doing an AES encryption. So one would be the key expansion. So it is called the round keys, and which is derived from the cipher key using the key schedule. And I will be explaining the same in the coming slides. And there would be an initial round wherein the add round key. So each byte of the state is combined with the round key using a bitwise XOR, and the rounds. So these rounds consist of 4 steps. One would be sub bytes, which is a nonlinear substitution step. And the next would be the shift rows, which is a transposition step. And the next would be the mix column, which would be mixing the operation of each column. And there would be an add round key. And the final round, it again would be sub bytes, shift rows, and add round key. And there is no mix column in the last round. So it depends on like when we are going to use 128-bit key, 10 rounds would be used, and the final round, after the 9 round, the final round, there won't be a mix column. So this again is a detailed structure of how the key expansion happens when we get the cipher key, and the plain text, how it is transforming with the add round key and each round, and how the inverse would be calculated in the reverse way. As I have mentioned earlier, like we are talking about symmetric cipher, and AES encryption is a symmetric algorithm. So we would be using the same key, and all the rounds would be coming from, as you see that in the encryption, you could see that round 1 to 9 and then 10. And whereas when we do the inverse, when we do the decryption function, it would be the reverse way, like it will start from the round 10 and then ending up with round 1 to get the plain text back. So let me just explain how a 128-bit value would be viewed, or how we'll be processing the data. So if typically, if you could just see like a 128-bit value, hope everyone would be knowing what a bit is. It is nothing but it could be 0 or 1, a binary thing. So a data block would be used. All the operations would be looked as a 4x4 table, with each box would be having a 1 byte. So the representation as a 4x4 matrix. So each box will be having a 1 byte, which will have 8 bit. So the key is expanded with an array of 32 bits words. So I'll be explaining in detail about the same. So how a data unit would be a byte. These are all very fundamental thing. I just want to step in if there is any clarification required further to this. So a byte, it would be like will be just telling us B0 to B7, and you could see like a B can be represented as a column or a row, and a word is nothing but a 4-byte combination. So that is like a B0, B1, B2, B3. So we would like to process the key expansion in the name of words. So that's why we need 2 type of representation. So the data units, the representation, these are not just representation in order to understand how the encryption happens, in order to understand the internal structure of AES. And when we want to do in a software, we need to code it. So these and all could be like, it would be similar to looking like a pseudocode, how you would be representing the data. So in line with that. So these are all the standards which generally we follow when we describe AES. So a block, typically a 16 byte, so B0 to B15, wherein it will be a 128 bit would be divided into 16 bytes, and those 16 bytes we would be representing as a state matrix, and each position will be S00. So it will be like a 0 row and 0th column. It will be the first row, second column. So it will be like that. So you could just see a state matrix, and this could be as also represented as a 4-byte thing, 4-byte. So something like W0, W1, W2, and W3. So these are all the two type of representation, because we'll be doing operation certain things in terms of bits, in terms of bytes basically, and in terms of words. So the representation is done in both way, as byte as well as the word. Is there any clarification required in this slide? Hope everyone would be understanding this. So let me just again tell how a block would be. Like the 128 bit would be looking as like B0 to B15, and each byte would be having an 8 bit, and those things would be like written as a state matrix, which would be like B0, B1, B2, B3, varying till B15. So the operation, so these are all the representations which I had just explained in the previous slide. In order to have a further clarification, just have a look into this slide. So let me just again in briefly, if you have a plain text, say like AES uses a matrix ZZ. So this is a plain text like AES, USE. These are all the typical English alphabet. And first thing we would like to do is the plain text would be converting into hexadecimal. We'll be viewing this plain text as a hexadecimal thing. So you will have a standard representation, A, E, S, and all the stuff like that. And the same thing, the plain text would be viewed as a state, and it will be written in this form like 00219. So this is a plain text. How we'll be viewing a plain text in hexadecimal and converting into a byte and looking as a state like that. So we will be representing a plain text as a 4x4 matrix like this. Hope this is clear to everyone. So let me just enter into detail of each round. So as I have mentioned earlier, so each plain text, the input would be the plain text, and the plain text would be a 128 bit, and that would be looked into as a 16 byte, and that would be again looked into as a 4x4 matrix with each byte arranged over there. And we'll be looking into, so the state is something like the input, and that would be going to sub byte. So this is the first step which will be using in the AES round function. And after the sub byte, again, we'll be calling intermediate value of all the AES steps. So once the plain text, immediately before starting the encryption, we'll be telling the plain text as a state. And after undergoing each transformation, the intermediate thing we'll be calling as a state. So the first state that you could see outside the encryption block, outside the round function, would be the plain text. And once that enters, it will be undergoing the sub byte. That is an operation that I would be explaining in detail in the coming slides. And then it will be going after the sub bytes. We'll be again telling that as a state. We'll be arranging the byte as a 4x4 matrix, and it will be undergoing another operation, shift row. And then again, we'll be calling that as a state, and it will be undergoing another operation, mix round. And again, the intermediate result would be calling as a state, and it will be undergoing another operation with add round key. And the output which comes from each round would be again any intermediate value, or any set of 128 bit which undergoes the transformation in between the rounds and after the round. We'll be calling this as a state. So one add round key is applied before the first round, and the third transformation is missing in the last round. So the thing is that there won't be a mixed column in the last round. So this is what we have said in the earlier slides. So let me just brief into how the operation would be. The first operation which we undergo in the AES would be the sub bytes. So for this, we need to understand it is basically a simple substitution, which makes the very important theory of confusion. So the thing is that we'll be using one S box, that is called substitution box, of 16 by 16 byte, containing a permutation of all 256 8-bit value. You could see that any 8-bit value, there could be like a 256 bytes what possible, the possible permutation. So we are particularly making one permutation, one particular type of permutation. I'll be explaining in detail how that permutation is, how we are choosing an 16 by 16 matrix. So each byte of a state is replaced by a byte indexed by a row, like a left 4-bit would be indexing as a row, and the column, the right 4-bit will be indexing as a column thing. So for example, a byte 95 is replaced by a row 9 and column 5. So which has the value 2A. So we'll be I'll just look into, just show an S box. So here you could see a lookup table. So if you are getting a byte of 00, so we'll be taking the first 4-bit, so 0 and 0. So we'll be substituting 00 byte as 63. Suppose if you want to substitute, if you are seeing a state matrix as a byte would be BC, so it will be like B. We'll be looking here B, and then we'll be corresponding column. We'll be looking into BC. So the value, the BC would be transforming into 65. So this is a simple lookup table. So this is what I have just mentioned earlier. Like each how a substitution box, how a 16 by 16 byte like a substitution box, how we will be replacing a byte with another byte with a lookup table. Now let me just tell how this transformation is happening. So how we are going to this, how each byte is transformed into another byte. So how this S box is constructed. So this is done using a defined transformation of values in Galva field, that is a GF2 power 8. You all would be familiar with Galva field. So like, let me just brief into how, hope everyone would be knowing what exactly a finite field will be. Like it is like making a field of any number. Like as you all know, there is now, if you have GF2 to the power 8, so that is 256 with a set of 256 bytes, we won't be able to cover up two operation to make it a field. So in order to make a field, we'll be using GF2 to the power 8, wherein a bytes, wherein we'll be taking a irreducible polynomial of degree 8, and we'll be using the operation. We'll be defining an operation multiplication in line with that. So let me just define and how a finite field representation, how it is related to each byte, the coefficient of each where this polynomial, you could just see like B7, B6, B5, B4, etc. B0. This thing is basically a byte that we are going to transform. Say suppose we are having a state byte as 95. So here you would be like say 63. So here he will be like 0110 and 0011. So you could just look into as a polynomial of degree 7, and you could just these are all the coefficients. So you could just see that 01100011, a byte you could just represent we are trying to represent each byte as a polynomial of degree less than or equal to 8, and so that we'll be able to represent all bytes in terms of a polynomial coefficient. And these polynomial coefficients will be defining, and will be taking a help of a finite field. We'll be defining operation addition and multiplication, and we need to use a primitive polynomial that I'll be explaining what primitive polynomial we will be using that. So before that, let me just introduce the addition. Addition would be normal XOR function. So how a byte operation is defined in line with finite field arithmetic. So each byte would be just, as I have told, we'll be representing a byte, say 57 is nothing but a 8-bit value, and we'll be there is a corresponding polynomial with degree less than or equal to 7, less than or equal to 8. So that will be like x to the power 6 plus x to the power 4 plus x to the power 2 plus x plus 1. So this is a polynomial representation of a byte. Hope this is clear to you. Similarly, the another polynomial, another byte we would be representing in this way. So how a finite field? So we are trying to look into each byte of AES. that is for this encryption, we are trying to represent each state byte as a polynomial, as we are trying to represent those bytes as a coefficients of a polynomial. So it would be like how an operation would be like a byte XORing would be, the addition would be XORing. So those XORing like 57 XOR 83 would be like, it will be just a byte XOR and sorry, bit XOR, and it would be like 0 XOR 1, it will be 1, and in the second thing like 1 XOR 0, it will be 1, 0 XOR 0, it will be 0, and in the fourth term 1 XOR 0, it will be 1, and in the fifth term 5 XOR sorry fifth term 0 XOR 0, it will be again 0, and in the fifth one 1 XOR 1 XOR 0, it will be 1, and 1 XOR 1 will be 0, and 1 XOR 1 would be 0. So this is how an operation is defined. So XOR operation like 57 XOR, a byte XORing would be just similar to the bit XORing, and we are trying to represent that as a coefficient of a polynomial. That's the thing. And multiplication, when we want to multiply two polynomials, definitely it is getting over the degree x to the power 8. So we won't be able to represent as a byte. So we need a result over here as a polynomial of degree less than or equal to 8. So in order to doing that, we need to have a polynomial. We need to choose a polynomial, an irreducible polynomial, which is primitive, so that we'll be taking modulo of that, so that we'll be getting a byte. So this polynomial, the polynomial which AES is used, is x to the power 8 plus x to the power 4 plus x to the power 3 plus x to the plus x plus 1. So this is an irreducible polynomial. So there are like plenty of irreducible polynomials possible. So they have chosen, like the AES designers have chosen a polynomial, so that we'll be having, when we do multiplication operation, we'll be, when two bytes are multiplied, like as I have mentioned earlier, 2 bytes would be like a coefficient of the polynomials of degree less than or equal to 8, so that we'll be resulting a polynomial which would be of degree less than or equal to 8. So we'll be again possible to represent byte multiplication resulting into a byte. Hope this is clear. So let me just again tell you in a brief way, like each state would be like a byte, which will be like a plain text, and how each byte would be transforming. Like we'll be taking that byte and we'll be finding an inverse for that, and this thing would be like finding, and there is a matrix associated with the linear transformation. So we'll be finding, with respect to irreducible polynomial that we have chosen, we will be able to transform a byte with another byte with this matrix, and that will be XORed with another constant, and that will be the result of a subbyte. So this is what exactly happens into subbyte. So I hope this is clear. Each byte would be will be taking the inverse, and I have told how the inverse would be, like they need to be XOR, and we need to find there is an irreducible polynomial associated with that, and that transformation will be able to do that by multiplying a 8 by 8 matrix. So it will be like a byte would be transformed into another byte and will be XORing with a constant. So that is the transformation that we are going to do in a sub-byte thing. So each byte is transformed into a new byte, and each byte is transformed into a new byte with this step. So, and the reverse way, it will be the same, similar to that, wherein we will be having a reverse matrix multiplication, and instead of XOR, there will be a minus for that. So again, the the inverse of XOR would be, in order to get back that, we'll be again XORing it. So the substitution sub-byte and inverse sub-byte operation is defined in this way. So let me just again look into, like when we want to implement it, a sub-byte operation involves a 16 independent byte-to-byte transformation. So we'll be taking a state byte and we'll be looking into an 16 by 16 lookup table. So each byte will be taking X as the first 4-bit and Y as the last 4-bit, and we'll be taking that substitution and we'll be directly substituting another byte. So we'll be this is what happens. So in the AES, how the operation is defined, and we have a predetermined substitution byte in line with the chosen polynomial. So the thing is that any byte will be transforming into another byte with this lookup table. So this is what the pictorial representation of the same. So this is the lookup table, and this is the inverse substitution byte lookup table, wherein this will be used for decryption. And a sub byte, suppose we are having a state matrix like this, as we were just started up with let me just show you. So this is what we have started up, the plain text as AES uses a matrix CC. So this is a state matrix. So when we use this state matrix, this is a plain text. This is a plain text. So after the transformation of sub byte, after doing all these operations, so we will be changing the state into a new state. After using the sub byte, this will be the new state. So this is the first step which happens. So each byte is transformed into a new byte in the sub byte transformation. Hope this is clear. And during the inverse transformation, each byte would be using the inverse substitution table, so that we'll be getting back the same state again. So this is the another operation, shift row. So initially we'll be having a state, and those state is transformed with the sub byte operation, and the next operation would be shift row. So shift, it will be like shifting which permutes the byte. So I have just colored it so that it will be easy to understand. We'll be using a circular byte shift in each immediate. First thing would be like first row would be remain the same, and the second row will be like one byte circular shift to left. So that you could just look into that, so that we'll be having this yellow, green, and blue. Then we'll be having that circular shift. So this first thing would be going to the last. So similarly, the third row does 2 byte circular shift, and the fourth row does 3 byte circular shift. So in the encryption, the transformation is called shift rows, and in the decryption, the transformation is called inverse shift rows. So we are doing nothing but shifting the rows. So the first row will be remaining as the same. So after the sub byte transformation, again we'll be having a state matrix. So in the state matrix, so first row would be remain as the same. In the second thing, we'll be using 1 byte circular shift to left. In the third row, we'll be doing like 2 byte circular. So these two will be moving here. And the fourth row will be having 3 byte circular shift. So 3 byte, like this red, yellow, and green would be going to second, like first, second, third would be going to second, third, and fourth. So this is how another representation, like each state would be doing like the first row remains the same. So S00, S01, S02, S03 would be the same. In the second row, we'll be having one thing. So it will be like S10 would be going to endpoint. And the third thing, you'll be having two byte, and the fourth thing will be having a 3 byte. So this is like we'll be calling as 1 byte circular shift, 2 byte circular shift, and 3 byte circular shift. Hope this is clear. So we have the state over here after the substitution matrix. So this will be after the shift row, how each row would look like. The first row remains unchanged. In the second row, you could see like there is a transformation. The F2 goes over here. And in the third row, there is a transformation, C9 and C9. The both first and second would be going to third and fourth. And in the fourth row, you could just see the difference, like FA6382 would be replaced in from the second, third, and fourth position. And the inverse would be exactly the same, similar to this. So another transformation which is very important, which comes into AES, is mixed column. So the shift rows and mixed column provides the diffusion to the cipher. So I'll be explaining what diffusion is like. And each column is processed separately. So each byte is replaced by a value depending on all the 4 bytes in a column. So again, here we will be representing each column as a polynomial of degree less than or equal to 4. So like X, Y, Z, and T. And there is a matrix association. We'll be multiplying with a constant matrix, so that each column will be transformed into a new column. So this is how it happens. If you multiply with a 4 by 4 matrix, so there is a matrix associated with this linear transformation, and each column, the S00, and it will be after the transformation, the mixed column transformation operates at the column level, and it transforms each column of the state to a new column. So each column S00, S10, S20, S30, after undergoing this transformation to S-00, S dash, it's just a representation, we'll be getting another byte. It just. So this is the transformation which is going to happen for our example. So, and the another step would be add round key. So add round key would be, we'll be XORing the state with 128 bits of round key. I'll be telling how the round key will be extracted from the encryption key. So add round key proceeds one column at a time. So adds a round key word with each state column matrix, and the operation is matrix addition. So inverse of the decryption will be identical, because since XOR own XOR's inverse itself is an XOR, so we'll be doing again the XOR function to get back thing. So this is the structure. We'll have the add round key, we'll have a state matrix, and I'll be explaining how these words would be, how we'll taking an add round key, and which will be again a state matrix, so that we'll be getting a resultant state after each round. So this is a pictorial representation of how an AES round would look like. So as I told, a state 16 byte would be there. It will be undergoing sub byte transformation, whereas each byte would be transforming into new byte, and that again would be telling us a state. And from there we'll be doing shift rows, as I have told you earlier, like shift row combination, whereas the byte would be shifting from the rows, and it will be under the resultant would be another state. So each resultant after each operation and after each round will be telling us a state. So this state 16 byte would be undergoing mixed column transformation, so that we'll be getting another set of state wherein it will be mixing up the columns, and again we'll be undergoing add round key, that is XORing the state byte with the round key, whereas we'll be getting a result as a state. So this is how each AES round would look like. So let me just tell you what do you mean by the confusion and diffusion. So this is nothing but the two essential concepts in cryptography, which is particularly in the design and evaluation of block ciphers. So confusion is nothing but, from the name itself, it is understood that confusion aims to make the relationship between the plain text and the ciphertext as complex and unpredictable as possible. So it involves like introducing these nonlinear operations like a substitution box, as we have seen here, and substitution to obscure any statistical patterns or correlation between the input and output. So the goal is to increase the complexity of cipher's behavior and make it difficult for an attacker to deduce information about the key or the plaintext from the ciphertext. So typically a confusion is achieved through operations such as substitution boxes, especially in the substitution permutation network. That is another design strategy of block ciphers. So S-box introduces nonlinear mappings between input and output bits, which making it challenging to deduce the relationship between them. So SPN is nothing but substitution permutation. With this operation, combining the substitution and permutation in multiple rounds will increase confusion. So confusion and diffusion is the major part, which basically this is nothing but making as complex as possible while doing the operation. There need not be any correlation, like we should not be able to find a relationship between the plain text and ciphertext. So how this is achieved, as I have told you, we could see that the transformation, what and all is happening in each round. You could see each round of AES, besides like sub bytes, shift row, mix column, and add round. So with these operations, we'll be able to make confusion and diffusion in the cipher, which is important to make cipher non-attackable. So diffusion aims to spread the influence of each bit of the plain text or the key throughout the entire ciphertext. So it ensures that a small change in a plain text or key produces significant changes in the resulting ciphertext. So diffusion is nothing but the key, the cryptographically secure key, is diffused with the plain text such a way that we won't be able to find any relationship. Something like if there is a 1-bit change in the plain text, or if there is a 1-bit change in the key, the resultant cipher will have more than 50% change in the output. So that is called the diffusion is. So the diffusion is achieved by applying operations that that will influence the individual bits over a wide range. So something like one commonly used technique for diffusion is permutation. So which shuffles the bits of the plain text or the intermediate state, such that another technique is mixing it, like where the bits are combined and transformed in a way that maximize the spread of influence. So I would be just explaining in detail about the same. Like if you just look into shift row, we are moving the bytes from one position to another position. Similarly, when we look into first state, like substitution byte, each 4-bit is transformed into another 4-bit, so that each byte is transformed into another 4-byte. So the key is mixed in such a way that we achieve both diffusion and confusion with these steps. Is there any doubt in between that? Hope everyone is able to follow this. Okay, let me just tell how AES key scheduling would be. So the key scheduling would be again the 128 bit, like a 16-bit key. There will be a cryptographical key, which is randomly generated, and those keys are we need to make as a 44 set of 32-bit words. So as I have told you, each word would be of 4 byte. So a pre-round will be representing as 4 word. Each 16 byte of key would be representing as W0, W1, W2, and W3, and we'll be expanding based on the number of rounds required. Say AES 128, if you're taking as 128 bit key, there will be 10 rounds. So we would be requiring W0 to W44. So a cipher key, again, it will be a byte, like K0 to, we'll be representing the key as K0 to K15. And how this key expansion process happens is what this is about. Like you could see that, yeah, as I have told, each word would be, so we'll be combining K0 to K3 as one word, K4 to K7 as another word, K8 to K11 as another word, and K12 to K15 as another word. So how the transformation is happening for each word, this is the transformation which is happening. Like it will undergo a rotation like rote word, and it will undergo a substitution byte, and there will be a constant XORing, and that will be another word. So let me just tell how T4 would be. We'll be making like T4, T8 till T40. How we are going to make, I'll be expanding that key expansion submodule. Like a rote word performs a 1-byte circular left shift on a word. For example, something like if there is a word like B0, B1, B2, B3. So that would be transformed as B1, B2, B3, and B0. And subword, it's exactly a substitution with the help of SBox. We'll be substituting a byte, each byte of input word using the SBox. So B1, B2, B3, B0 would be again transforming into like B-1 and B-2, B-3, and B-0. And the next would be like a rote word. So it will be like XORing with a round constant. So, and the round constant would be like again another word. And it is like each round constant, for each round we'll be taking as, for the first round, we'll be taking as the first byte as 0, 1, and the other 3 bytes would be 0, 0. So for each round, the round constant word would be like first round, it will be like 0, 1, and another 3 bytes would be 0. For all the other rounds, you could just see that only the changes would be in the first position. In the word, the first word would be transformed into, for the constant would be like 0, 1, 0, 2, 0, 4, 0, 8 until it goes to 36. And again, the multiplication is defined over GF2 power 8. As I have told you, the entire structure of AES depends on, we'll be seeing each byte as a polynomial of degree less than, a coefficient of polynomial of degree less than or equal to 8. So this is an example like how a ciphertext key, suppose we are having a random key like this, like 2B7E like that. and we'll be taking this as, we'll be considering each word as 4 byte. So 2B216, this will be considering as W0. Hope everyone will be able to see this. W0 and W1 would be like from the fourth, like from 28 AE, D2 and A6. So each word would be 4 byte. And how each transformation happens, like we'll be considering this word, and how the transformation happens is what I have just explained in the previous slide. So this would be just confusing because I have just put the exact value what in line with the ciphertext. Like we'll be able to understand the each operation in a better way if you just take a plain text by yourself and do the transformation in a book and paper, so that how the transformation happens, how each bytes are changed, how each bits are changed, how this confusion and diffusion is happening after completing each transformation. So I have made an example, like say if you are taking the key, like cryptographically secure key, as like that's my kung fu. So this is we'll be considering this as each 1 byte, so that it is a 16 ASCII character. So that's my kung fu. So that will be transformed as a hexadecimal. We'll be having a 16. Hope everyone is able to see this. So I'm taking as a key. So generally, before doing an encryption, we should have an cryptographically secure key. So I have taken this as a key, and that key is taken looked into as an ASCII character, and we'll be transforming it to as a. I have taken exactly 128 bit, so that we'll be having a 16 byte like this, like 54 till 75. So a key would be like this, and the plain text which we are going to transform, which we are going to encrypt, is like 2192, and each space will be again considered as a byte, so that you could see that a space is considered as 2020. You could see that. Okay, so the plain text in English would be again in line with the 16 ASCII character. We'll be transforming into byte. And right now we are going to use key as that's my kung fu, and we are using plain text as 2192. Let us see how this is just a quick overview of how the transformation happens as I was showing the example. So it is like the first row would be like a key would be transforming what I was explaining earlier. Like we'll be making a key. First thing would be we'll be considering each key as W0, W1, W2, W3. And first thing what we'll be doing before starting the encryption is we'll be expanding all the round keys. We'll be generating all the round keys, so that we'll be able to use that after each round, for each round. So first we'll be generating set of keys. So these are the round keys, like round 0 to round 10. Initially we have made with respect to our example. So we have got from the key, that's my kung fu, we have expanded and made 11 set of keys out of it. So this is the first step that we need to do. And then we'll be starting our round function, wherein we'll be looking into as a round key we'll be taking as the first round key, and we'll be XORing with the state matrix. So this is the plain text that we are having, and that is the start point. So the current state would be like that. The first round starts with substitution byte. We'll be using, as explained earlier, we'll be having a lookup table, and those lookup table, those byte is generated with the help of Galva field. So the thing is that each byte would be transformed into another byte with the help of lookup table, and you could just see the shift row again happening, like a 63 EB9F A0 would be like there is no change in the first row, and the second row, like it will be like left by offsets by 1. Like we'll have 2F9392, and then C0 would be going over here. We will have 2 shift here, and in the fourth row we'll be having a 3 shift over here. So this is just an example, just to see, like we'll be able to do it in hand if you take a paper and pen, and if you try out by ourselves, we'll be able to understand how this transformation happens. So as we don't have much time, so I'm just giving an example how the transformation happens after each round for each byte. So mixed column, again, I have told you there is a standard 4 by 4 matrix. If you multiply with this 4 by 4 state thing, we'll be getting a new 4 by 4 state. And similarly, each transformation is done in line with the primitive polynomial that is taken. So this is what the mixed column would be. And again, the round key would be like XORing. So each round, these are all the transformation which happens. So you could see that how the bytes are changing, and ultimately we are getting into result as a ciphertext as 29C3 etc. till 3A. So this is just an example. I just want to showcase like how a transformation would happen after the AES operation. So in order to understand a little bit like how the transformation happens in terms of how the AES specification is, like as I have told you, each byte would be like it is a standard document. You could just it is just a representation like how in detail, if you someone would like to know how the transformation is, how each byte is considered as a polynomial of degree less than or equal to 8, and how the regional state would be. What I have told earlier is just again a detailed explanation of what how the finite field operations would be. Like as I told you, addition would be XOR, and finite field multiplication would be like choosing an irreducible polynomial, so that multiplying 2 byte and we'll be taking modulo of this irreducible polynomial, so that we'll be getting a byte. So this is just a mathematical explanation of how we have to do an operation to attain how the substitution byte is evolved, or how the computation happens. So, and ultimately we'll be having a lookup table, like each thing would be like transforming into another byte. Each byte would be transforming into another byte. And there are other things like for testing testing how statistically good are an AES would be. So there are certain standards, there are multiple tests associated with that. And one of the very famous research article which uses to do an automated statistical method for measuring the strength of block cipher is from these people. And this is very acclaimed research article wherein there is a automated tool. We'll be able to make a software out of this, and we'll be able to test each bulk of like a block cipher which is encrypted with this by doing a program out of this. And there is another statistical suite which generally used for random number testing, which again could be used for testing our block cipher thing. And this needs a lot of time to explain each test how it would be. And I just want to give a glimpse of these are all the tests, statistical tests which we generally do for random number generation, or which we test for random number, which could be tested for each ciphertext. So each ciphertext we could use like frequency test, like how many ones and zeros are there. Suppose we are having a 128-bit ciphertext, and approximately in line with the frequency test, we are expecting that statistically it is like we'll be having something like half set of thing would be 1 and half set of thing would be 0. So a frequency monobit test would be like out of a cipher 128-bit, we are expecting like nearly 64-bit would be zeros and 64-bit would be ones. And the frequency text within a block like will be again like a 2-bit test, something like how much patterns are there, like how many zeros are there, how many combining 2 bits, like how there are like 4 combinations possible, something like 00, 01, 10, and 11. So what we are expecting from a ciphertext is there is exactly like equivalent to some 32 set of 00s would be there, some 32 set of 01s would be there, some 32 set of 10 would be there, and some 32 set of 11s would be there. So that's like we would be able to test again with a 3-bit thing, and there is a run test, and it needs a lot of time to explain. These are all basic statistical tests of randomness, which we would be able to test every output of a AES, and which generally passes all these tests. And let me just get into what exactly, like again going back to the fundamentals, like what is our security goal of, like if we are having an encryption thing, at least need to communicate through internet, some message say M, and what are the security goals would be, we need data privacy, like there should not be any adversary, like should not be able to read the message. This is the fundamental thing. And the other part would be data integrity, like there should not be any loss of data, there should not be any modification. Suppose we are sending a message like I'm coming in between through the internet, it is going to be something like I'm going, and it is someone is intruded in the internet, there should not be any modification in between. So these are another expectation, these are the another basic security goal that we expect, like when we want to do a secure channel transmission. And another thing would be data authenticity. So the message M really originated from the person. So that is, so these are the three data or security goals. Like one is the privacy, and one is the integrity, and another one is the authenticity. What I would like to tell is the encryption standard, what AES will be able to use AES for all the three goals, all the three security goals. So again, I just want to expand, like how a design of block cipher would be in line with our AES thing. So we'll be having a set of key, like it will be again bits. So K would be like how many number of key bits are there. So suppose we are having a plain text, say 0 to 1. Suppose if say in the AES 128, we would be taking as like a plain text would be like 128 bits, so that we'll be having bits of 0 to 1, 128 things. So N would be like 128, and the combination and the key would be again K, the small k would be again 128. So with the help of key and the plain text using our encryption function, we'll be getting a ciphertext which would be same as the length of the plain text. So this is how a general architecture of a block cipher, how a block cipher will look like. So in the case of AES, as I have seen, if we are taking a key, like we can take any length, like this is a general structure of a block cipher. So we could take as a key of 80 bit, 128 bit, 192 bit, 256 bit or more. Right now we started using 512 bit as well. And again, then like plain text will be taking block, we'll be considering a block as 64, 128, 256. Again, it depends. So this is a general architecture, like we could fix the plain text block as like how many bits are there, and we could fix the key block as how many bits are there. And generally the plain text, whatever we are doing it, generally in line with that, we'll be having the ciphertext. So if we are going to encrypt a 128-bit data, the output would be a 128-bit ciphertext. So that's how the N remains the same. So in the case of DS, before AES there was DS. So in that, the key length would be 56, and the block size of what they were encrypting is 64. For AES, as I have told you, like we'll have 128 is the standard, wherein keys could be 128, 192, and 256. So each algorithm has got a lot of operations, and like the thing is that I am just generally telling how a structure of an encryption algorithm would be, and how a structure of block cipher algorithm could be, and how the round function come into picture, and how we'll be incorporating the confusion and diffusion with the round function. So this is how generally a block cipher would be. From the key, from the cipher key, we will be expanding the keys, and each keys would be using this is a generic architecture of block cipher. Any block cipher, say, generally would be designing in this way. Like from the message, we'll be manipulating from the key, we'll be making a set of keys from transformation, and we'll have a round function, R&D, like which would be like using the key and the message, where the message would be undergoing transformation with the help of round key in each round, and ultimately resulting into ciphertext. So in the case of RES, like there are 16 rounds. In the case of AES, there are 10 rounds if you are taking key as 128-bit, and it would be 12 rounds if you are taking the round key as 192-bit, and it will be 14 rounds if you are taking 256-bit. So the thing is that if we are having an encryption of messages of 128-bit, it will be transformed into decryption function and the reverse way. So we usually want to encrypt messages of arbitrary length. So splitting the message into multiple 128-bit block is not secure. Basically, like we won't be able to get exactly 128-bit of data which need to be encrypted. As earlier, for an example, I have used exactly 128-bit. So what exactly in practical thing, how we would be addressing this? So in this case, we would need the mode of operation, how we need to use our encryption, how we would be using our plain text and key in line with that. So this is called mode of operation of block cipher. The correct view would be like block ciphers are not just encryption schemes, that block ciphers are primitives which used to construct many other things. As I have told you, block cipher could be used for data integrity. Block cipher could be used in the earlier what I have just seen. It could be used for privacy, it could be used for integrity, and it could be used for authenticity. So what a mode of operation would be? A mode of operation which describes basically the process of encrypting each of these blocks under a single key. So I'll just quickly go through what are the block of what are mode of operations that we have. Earlier we had like ECB, CBC, CFB, and OFB, and right now what we would be using is authenticated contour mode, that I'm just not telling this right now, but these are the general mode of operations which has got like evolved across time. And for each mode of operation there is an advantage as well as disadvantage. So let me just briefly tell about the electronic code book, cipher block chaining, cipher feedback, output feedback, and contour mode. So what this is basically, mode of operation would be like processing of encryption, like how we'll be processing with a single key. So we'll be having like for electronic code book, how the key would be using. For cipher block chaining with one key, how we'll be doing the encryption. So this mode of operation is basically how efficiently we could use one particular key for doing a block of 128-bit, or say a block of plain text. So for this, the many techniques would be like we'll be having initial vector, we'll be using nouns, we'll be using padding, and these and all are various techniques in order to fulfill, like in order to make 128 and do the start of the encryption. So in electronic codebook, the message is broken into exactly like independent blocks which are encrypted. So each block is a value which is substituted like a codebook. Hence, like we'll have a ciphertext and encryption and the plain text. So secure transmission of single value. So it would be like how electronic codebook would be. Exactly, we'll be taking 128-bit and we would be using 128-bit key and resulting into ciphertext. So for this electronic code book, what we need is we need different keys in order to look different cipher. So if we have a plain text in the electronic code book, if we are using same key for multiple encryption, if the plain text is same, we'll be resulting into same ciphertext. So electronic code book style is for each plain text, there would be the same key would be used. So if you are using same key, if there is different plain text, there won't be, will be resulting into different ciphertext. But what is the drawback is if we are using the same message is getting encrypted. Suppose we are trying to do a testing and we are taking a plain text as all 00, and in the electronic code book way, it will be getting the same ciphertext because we'll be using the same key. So this this electronic code book could be used for encryption of some short pieces, something like exactly 128-bit. So there won't be any changes. So if there is a block of 128-bit of plain text, electronic code book is not advised to use. So this is a general thing, like 128-bit would be there and same key would be used for encrypting the set of all blocks. So which is not advisable. So this is the typical drawback, what I have said. If we are encrypting same message over and over again with the same key, we would be getting the same ciphertext, which from that intruder would be able to identify that, like, oh, there is something like the same text is manipulated. The message is something like which is unique. So electronic code book won't be able to use when we want to encrypt more than 128-bit, more than a particular block. Similarly, cipher blockchaining would be like we'd be using an initial vector, and what that would be XORing with the ciphertext, and those IV would be XORing going forward. So this is like how efficiently we would be using with one set of key, how we would be using a bulk of data encrypted using a one set of key. So cipher blockchaining is after every encryption, we'll be using this transformation. We'll be XORing with the previous ciphertext data, and those thing would be considered as IV. And this is how, like you could see that here, after the plain text, after the first encryption, in between here, we will be taking this as an output for using the next key. So the same key would be using in this way. So this is called cipher. This is called cipher blockchaining. So we are using the previous cipher output as a key for the next plain text. Hope this is understood. Similarly, this is like how efficiently a key could be used. So for block, if you want to encrypt a bulk of data encryption, we could see that cipher blockchaining for with one set of key would be able to encrypt a set of block of data. So after the initial expansion, after the initial encryption, like using key, what the ciphertext that we get after encrypting first 128 bit, those cipher output would be used as a key, like we would be XORing it before going into the round function. So this is like how efficiently we would be able to use the same key, but we are putting a random, we are generating an additional output so that each key is getting expanded into other way. So the encryption of a block depends on the current and all blocks before it. So this is another drawback of this cipher blockchaining. So this is the thing. So each mode of operation has got its own drawback. So I'll just quickly go through like another mode of operation. Like again, there is like cipher feedback mode, and there is output feedback mode. These and all are how efficiently we would be using the key. Output of 128 bit would be used for encrypting the further data. So that it is like same key could be used so that we'll be able to generate bulk encryption possible with one set of key. So each step has got its own advantages as well as disadvantages. The contour mode is the most simple mode, and authenticated contour mode is what we generally use right now. So it will be like we'll be using an counter like with maybe nonlinear LFSR or many other random stuffs. We would be able to XOR with the plain text, and we'll be generating the contours like counter in between, so that the same key could be used for a set encryption of bulk data. So which is uses high speed network encryption could be done in this way. A counter is incremented for each block. You could see that how the picture is. It's nothing but no need to confuse. The thing is that we will be using like initialization vector and a contour. With the help of that, we will be utilizing a set of key for encrypting further set of data. After first encryption, we'll be using another, we'll be generating another pseudo random like data, like which would be used for further encryption with the same key. So each mode, like it has got its own advantages and its own disadvantages, and contour mode is faster and which is simpler, which allows parallel processing. And right now what we see, the bulk encryption happens over internet would be like a authenticated encryption mode. There are another further modes which NIST used to evaluate and which is made as a standards, and these are all the general thing, like how an encryption process happens with one set of key, how we would be able to use the same set of key with the help of manipulations. So this is called mode of operation. So that's the thing we need to understand for this. And a lot of slides I have added up. This itself takes a lot of time. Hope like this is the thing, like block cipher application, we will be able to encryption of arbitrary length data, like message authentication code for to do authenticated encryption, to do hash function, to generate cryptographically secure pseudo random generation, to do key derivative, function. So these are all the possibilities from a block cipher. So from AES, we would be able to generate, or we will be able to use for this operation. Like this and all are certain encryption standards which would be used in between. So these are the things. For message authentication code, we'd be able to use this block cipher. For authenticated encryption, we'd be able to use block cipher. For developing an hash function, we'll be able to use an AES or like any other block cipher to generate a cryptographically secure pseudo random generation. Like you could see like a Rowlet or many other online gaming platform, they used to have like a cryptographically or like a pseudo random number generation, wherein they would be using the standard AES or other standard block encryption algorithms. So let me just briefly introduce cryptanalysis. Cryptanalysis is something like, is it possible to break a cipher with the help of any possibility of vulnerability, finding the vulnerability in key or finding the vulnerability in application, how we are implementing it. So AES has undergone extensive cryptanalysis since its introduction, and it has undergone like most famous what you call list of cryptanalysis are. I'll be just briefing it. It needs a lot of time to expand what it is, like a differential cryptanalysis. So I'll just briefly tell what exactly is. So differential cryptanalysis is a technique used to analyze the behavior of block ciphers. It aims to exploit the differences in the input and output pair of plain text and ciphertext to deduce information about the key. As I have told you, the design and cryptanalysis go hand on hand. So what we were while doing and design of an encryption standard, a block cipher, what we were thinking of confusion and diffusion. The cryptanalysis of differential cryptanalysis would be exactly looking into, is there any input output correlation, is there any possibility of deducing key from the output, is there possible to extract the plain text. So there are the linear cryptanalysis would be another thing, like is there any linear relationship between the plain text, ciphertext and the key. So it is vice versa, is there any linear relationship between the plain text and key that could be evaluated, is there any linear relationship between ciphertext and key that could be evaluated. So this is again like another type of cryptanalysis. So this is again related to confusion and diffusion, which we have used for developing and designing a block cipher. So meet in the middle, again another type of attack, which would be like I have just briefed it how it is. Like there is a standard procedure and ready-made code is available in the internet, so that if we are generating a code, we would be able to do this cryptanalysis immediately from with the help of internet. So side channel attack, what it is, and there are like multiple attacks are there. I think I'm not getting into deeper into that, so that I think we will have a brief discussion on if there is any doubt in between, till now what it has happened, so that I could conclude this. So just to understand, there are multiple attacks. There are mathematical formulas developed in line with how a plain text could be attacked, how the ciphertext could be attacked in order to extract the key. Once we get the key, then it will be easy for us to get the plain text. And let me just come into like again getting very much fundamental into how the block cipher design comes into picture. So let us see, like ultimately we are working on bits. So let us see a function, encryption function could be like a n bit of data, something like 128 bit of encryption transforming into another 128 bit. So it is basically a permutation of bits. So encryption algorithm is something like, if we do a reverse of encryption decryption algorithm, we will be resulting into X. So basically, ultimately a bit will be a byte, bit or byte would be transformed into a bit, another bit or byte. So hope everyone would be knowing that a permutation of a byte, say this is a function. Suppose we are considering this as a function. A permutation should be like a 1-to-1 and on-to function. So I'm just telling how suppose we are taking 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. This will be a permutation, and this won't be a permutation, as we could see. Like it is not onto, like 0, 1 is again mapped to 1, 0, and 1, 1 is again mapped to 1, 0. So this is not a permutation. So what I just want to insist is, like, which security property should a block cipher satisfy? That is what should be a security definition of a block cipher looks like. So the one thing would be like the permutation should be hard to obtain. It will be very difficult to find this permutation. The what encryption function, so that we need to find. So these are the possibilities, like from the ciphertext, like is it possible to obtain from the first set of encryption set, or is it possible, suppose we are having two set of encrypted output, say y1 and y2, is it possible to obtain the key? That is it possible to obtain the permutation function? Again, is it possible to find the permutation function from the output, the set of output? So these and all are our suggestion, like what would be the one best combination of permutation function could be. So it goes on like that, like is it possible to have, like we need to have a permutation function. What I am telling is just in the previous slide, no, it will be every encryption function could be checked as a permutation. Like I'll just tell you after this. Like we could define, it is basically a pseudo. What do you mean by a pseudo random function, and what do you mean by a pseudo random permutation? So let us define a pseudo random function would be a mapping, like with the help of keys. Suppose say we are having a k set of keys, set of 0 1 k, and the set of input could be 0 1. With the help of key, with the set of key, and with the help of plain text, we'll be getting an output 0 1. So what exactly would be, like with k in and out are called the key length, input length, and output length. So think as a pseudo random function as a family of functions. So let us think as the input would be again a combination. So we are trying to define what do you mean by a pseudo random permutation. So what I would like to incorporate is, like every encryption function, every output would be a pseudo random permutation. Every encryption output should be a pseudo random permutation. So this would be this basic thing. Just I just want to insist how we'll be designing a encryption algorithm in line with the bit transformations. So every PRP, like a pseudo random permutation, would be a block cipher. What we are expecting an output of a block cipher is a pseudo random permutation. That's it. So I think with this I would like to conclude, because I think it's already getting time, and I would like to get few questions, or is there any doubt what I have just so far explained?
Thank you, sir, for the informative session. Before moving on to the Q&A session, participants please note the link to submit the feedback form of the session is shared in the chat shortly. Kindly submit it without a fail. Now the session is open for the questions. If you have any questions, free feel to ask here.
Actually, I have just added, like how in line with our block cipher development, no, how we would be addressing how is it possible to generate pseudo random functions. So this is something getting deeper into design strategy of a block cipher, wherein I have worked into. So it's basically how to generate a pseudo random function. Ultimately, our resultant could be like, is it possible to generate the best pseudo random permutation with the help of say some crypto primitive. So with the help of this, what you call like shift row, mix column, or any other pseudo crypto primitives. So I have made a detailed analysis, or how an expansion could be, and how random functions could be, that I have not dealt it in detail. So this is how a design strategies would be. So maybe if time permits, no, I would have just completed this. Again, it should not be like ultimately I would just want to give an intro that designing a block cipher with the help of mathematics, like with the help of a lot of field in the mathematics, is pretty challenging and pretty thought provoking, and it has got a lot of arena. Like we have got we will be able to generate a lot of research articles out of it, and we will be able to present our encryption algorithm in public. And what is the general standard which happens for cryptography is that we need to present our encryption algorithm into public domain, and the public would be able to defend it with their own cryptanalysis. So that's how the AES has become. That's how the AES, after undergoing so many years of cryptanalysis, till now AES 10 round is non-breakable. So the thing is that with the help of differential cryptanalysis, what I have heard is like with the differential power attack, the 7th round of AES could be attacked. That is again with the known plain text, like a known ciphertext attack. So the test would be, the cryptanalysis would be in line with a lot of restrictions happening. So in real life scenario, so far there is no attacks. So I have just briefed into how to construct in line with pseudo random permutation, how DES has evolved, and how the principles of DES of key expansion. So all that I would like to tell is it's all deduced to bits, and how you are able to make pseudo random functions out of the bits, like out of each block. Suppose say 128, say 256, or in future you could just, as quantum computation is coming up, you could just work on with 512 bit of key and 512 bit of plain text, how you would be able to generate confusion and diffusion in, and how efficiently you would be able to develop a pseudo random function out of it. So what I have in the field of cryptography, what we have discussed so far is a small bit which comes under here. You could just see that block cipher, and this block cipher, everything is interconnected, and what is happening in and around us, all the data exchange in and around through internet or securing data, when it comes into picture, all these points like digital signatures, hash functions, like MAC algorithms, all these are interconnected in line with block ciphers. So ultimately, I would just like to conclude that security is about how to prevent attacks, or if prevention is not possible, how to detect attack and recover it. Thank you.
Thank you, sir. If the audience have any doubts or questions, you are free to ask.
It seems like there is no question from the audience. Moving on, I would like to call Mr. Abubakar P to conclude the session.
I hope the audience got some idea about the internal structure and how the Galva field is used for its construction. And so, on behalf of mathematics department, St. Thomas College, and all the here, I express our gratitude to you, sir. Thank you all.
Thank you very much for inviting for the talk, and thank you very much for your patience for all the audience. Thank you.
With that, we conclude a remarkable and knowledgeable first day of our instructional workshop on advanced cryptography. Please be informed that the second day of the workshop starts at 5:30 p.m. tomorrow. Looking forward to meeting you all. Good night all.
Good night, everyone.
Good night.